Good morning, everyone. So we continue today on a major component of the module on fuzzy logic systems, which is known as fuzzy inferencing and fuzzy control. We have seen during the last lecture the notion of compositional rule inference, when we are able to combine basically the data context with the knowledge engine for fuzzy logic controller, which is going in part to affect the process. And we have seen how to compose these type of data context or data input with the knowledge engine and obtain an outcome of the system. And we have seen also the notion of min and the soup product as a compositional rule of inference for some of these implementation. The last part was mostly related to one particular representation of a fuzzy set and one particular representation of the outcome of the system. And we were able to create a relation that connects between the two, and then we apply the context that is different from what we have represented as antecedent and consequent, and we were able to find the outcome of the system. So this is what we are going to see today. We are going to see the extension of what we have started last time, and it is known as fuzzy inferencing and fuzzy control. So let me proceed with this here. Okay, so these are the three components that we are going to look in the next, this lecture and the next few lectures. I believe that on Friday we don't have a lecture, so there are no lectures on Friday. So our next lecture will be Monday next week. So we are going to talk about the notion of fuzzy reasoning. We are going to talk about the notion of fuzzy inferencing system. They are two different systems, as we are going to see. And then I will proceed with one or two case studies. And possibly in the next lecture on Monday next week, if we are not able to finish today's lecture on the various components, possibly we are one of the TAs will showcase you how to implement a full-fledged inferencing mechanism on MATLAB and possibly Scikit system. So that's where we are heading today. And let me start now on the notion of fuzzy reasoning and what we mean by fuzzy reasoning and how we are able to extend this notion to a knowledge-based system that is composed not only one single rule, but of multi-rules. So we are going to see that in the next several slides. So fuzzy reasoning in general is also known as approximate reasoning. So when you hear about approximate reasoning, it is, equivalent to fuzzy reasoning. So what is it? It is an inference procedure that derives conclusion from a set of if-then rules. So let's suppose that we have a whole set of if-then rules that are describing a particular process. And then these type of if-then rules, we are going to infer a conclusion, or what we call also a decision. So this is a decision. So that's what we have seen in the connectionist modeling. We would like to create a decision for a classifier. We would like to create a decision for a predictor if the output is not discrete. We are doing the same thing here. So the decision here is going to be a signal. This signal is going to affect a process, and that process is going to operate, is going to be actuated by this particular signal to generate an outcome. If that outcome is satisfactory, then the knowledge engine of the fuzzy inference system is not going to provide any type of feedback to the process. Of course, it's provide the feedback, but the feedback is going to be nil. Okay. However, if the output of the process is not satisfactory, then the knowledge engine, through all these type of rules and through the fuzzy reasoning, is going to create a decision type of signal that is going to affect the process. So remember in last time, so we said that this is the knowledge engine and this is the process. So, and both of them are interconnected with each other through a feedback loop. So this is usually what we call the controller here, the knowledge base of the system, and this is the process of the system. So this is the decision here that is provided by the system. So this is the process here, okay? And this is the knowledge engine. So fuzzy reasoning is an inference procedure that derives conclusion from a set of if-then rules. How to create this decision, how to create this conclusion, we are going to see it in the next several slides. So let us assume, so let's go back to the composition rule of inference, that we have a fuzzy relation on the Cartesian product of x and y. We are going to assume that we have a fuzzy set A in the discourse, in the universe of discourse given by x, okay? To obtain the resulting fuzzy set B, we first construct a cylindrical extension of ACA. So we are going to see all of that in the next few slides. But let me explain to you here, I mean, what we mean by this type of representation. So last time we spoke about the fuzzy relation, so we called it K. So now we are going to extend this because now F is going to be composed of not only one fuzzy inference, but of a fuzzy rule, but it's going to be composed of many of them, and we are going to utilize this. So we are going to look at this particular picture before we go to the composition rule of inference. So let's focus on this particular diagram here. So this particular diagram tells us that you have, a coordinate x system. So this is the independent variable, and this is the outcome variable. So we have a function that connects a map between y equal to fx. So this is not a decision, this is not a fuzzy system. So this is the discrete system that we have known through function analysis. So this is a curve, okay? So usually what we do when we have this particular curve that is constructed mathematically, that is constructed through data, that is possibly constructed through an interpolation or a prediction type of system. And then once we have this particular set of data that are representing y equal to fx, then for any type of elements that belongs to the independent variable a, we are going to extract the value of b. And how we do that? So we project a onto, y equal to fx, and then we project y equal to fx, value here, onto the system, which is going to be the decision. So the decision for our system here, when x is equal to a, is going to be y equal to b. So this is how we are extracting the image of a system. So again, we have here x, and is connected through the mapping by f. And then once we have structured this particular type of relation, then we can input any value representing for the universe of discourse, and then we extract b. So this is a very well-known type of process. So we would like to generalize this to a fuzzy logic system. So now let's suppose that we are dealing with a function, still a function that has a whole set of values. So it is not crisp function like this one. So we don't call it yet a fuzzy function here, but it is a function that is located over a full interval. So all these particular values are going to be potential functions for between the independent variable x and the outcome variable y. So this is what we are going to use. So in case when we are dealing with this particular function, so here we are not going to deal with the discrete elements of the independent variable, rather we are going to deal with intervals. So this interval is going to be, projected onto this particular function, and it's going to give us all these particular area here, okay? All these particular area of the function that are related to this particular interval, okay? So now, how we are going to obtain the output of the system? The output of the system is going to be projected onto the consequent type of function. So the consequent type of variable is going to be this particular interval b. So projecting an interval here through a function with many components here, which is an envelope of values, it's going to provide us with the output of the system, which is going to be an interval b. So this is only to showcase how we are going from this system to this system when we are dealing with a function that is not crisp, and when we are dealing with a value of the universe of discourse that is not one single point. So that's what we are going to do now in the extension of this particular system. So we are going to do now, we have, a universe of discourse, and this is universe of discourse X, and this universe of discourse provide us with all the values through this particular relation, which is given by F, and it's connecting between the universe of discourse of X and the universe of discourse of Y. So if we have here a fuzzy set, which is given by A, we would like to expect a value of F of A, which is going to be equal to B. Okay, so how are we going to obtain this B given the relation of F and given the function, the antecedent A? So we have seen how to do this composition rule of inference last time, but it was very particular case, and we didn't see why that soup main or soup product came from. So we are going to see it today, and we are going to see the extension of that particular representation, not only for discrete representation of fuzzy sets, but we are going to see it also for continuous representation and for the most general case. So this is one of the most important components of fuzzy reasoning in this course, I mean, which is related to the decision-making process. So to obtain the resulting fuzzy set B here, we first construct a cylindrical extension of A. Cylindrical of A. The inference of CA and F is going to lead to the antecedent of the projection of C of A intersect F. So what we mean by that, so we are going to look at it in a few moments, but in order for us to create this particular function B, there are a number of operations that we need to do. As we have seen in this particular image, in order for us to project A and to obtain B here, we have created this cylindrical extension. So this is the cylindrical extension of A over the function. So here, this cylindrical extension which extend, I mean, over all these parts. So this is a cylindrical extension of the interval A. So all of this is cylindrical extension. Now this cylindrical extension is going to intersect with this part of the function itself. And that particular intersection is going to give us a value of interest to us. But then how to migrate to the consequent type of variable? By doing a projection. So cylindrical extension, projection. So we have seen cylindrical extension of A in the past, and now we are going to do the projection of the cylindrical extension of A, which is intersected by F in this particular case, and this provides us with the value of the interval B. So this is to give you an idea why this particular type of operation that we are doing, and that's why we have studied the notion of cylindrical extension and projection, and which you are going to encounter them as well in assignment number 3, especially I think problem 2, where you are required to get the number of various type of projection for an n-ary type of relations. So that's a good problem that will make you even understand further the notion of projection over complex type of relations. So now these are the operations. So we have the fuzzy set A, we do the cylindrical extension of A, we do the intersection with F. This is what is, I mean, the antecedent of the system. I mean, so this is basically the transition antecedent, if you would like it. And then we do the projection P. So the projection P is projection of C of A intersected with F, and this gives us the outcome. So you see how we were able to go from A to B through all these particular type of operations, because we cannot do directly from A to B using one single type of operations. We have to go through certain type of operations. But when we look at this particular operation here and this particular operation here, each one of them is a relation on its own. So this is what we call relation R1, and this is relation R2. And we have seen also in the slides of the previous lectures how we are able to do the T-norm or the intersection or the composition of two relations. So the composition of two relations is no other than R1 composed with R2, known as the composition operator for this system. So this provides us with what is known as the fuzzy reasoning. So fuzzy reasoning is basically the extension of the well-known compositional of elements and functions. So this is the general type of representation of what we have seen last time in the area of compositional rule of inference. So this is the cylindrical extension of A, which has, incidentally, the same dimension as this particular type of relations. And last time, we saw that we can only compose relations when they are concordant, when they are compatible. What does that mean, compatible? They have a common type of dimension between both of them. Remember, so this is the F, which is the relation between X and Y, and this is the cylindrical extension of A. So they have one common type of coordinates between cylindrical extension of A and the fuzzy relation of F of X and Y. So this is the knowledge. Remember, this is the knowledge that comes from one or many type of rules, of if-then rules. So this is the intersection that captures that particular experience that a common operator of a machine or a system tells us to instruct us how to behave, how to operate when a particular signal is given within a certain type of range. So this is the possibility of all the description of the process. So one example, very, very simple example that I share with you here for an air conditioning type of system. So you say that, I mean, a rule could be like this. If temperature is warm, then air conditioner is high. Very simple. If temperature warm, here is warm, then air conditioner is high. Okay, so all of these type of values here are membership functions. Another one, if temperature is very warm, which is hot, then the air conditioner is going to generate very high level of air conditioning, which is value of cold. So we put all the type of inferences here, all the type of rules that could capture the possibilities of that particular process. So we can have a process, I mean, temperature is cold, then the air conditioner is going to be negative, which means it's going to generate heat. If temperature is warm, then it is high. If it is hot, then it's very high. So we have to capture all this type of information, which we call it knowledge, into a set of rules. Okay, so that's what we call last time the knowledge K, and we call it here for today is going to be the relation F between the antecedent and the consequent for many type of rules. So this translates the knowledge of the system. This is basically connects between the antecedents and the cylindrical extension of the antecedent, and this gives us the outcome of this particular intersection, which is the minimum. But this doesn't provide us with B. So this, what we have here, it's simply this particular area. So we need now to have the projection of this particular information to provide us with the value B. And that's where we are going to find that soup min that we have discussed last time in the composition rule of inference. Because you could have asked me last time, why did we have this representation of the compositional rule of inference in the form of soup min or soup product? So this is the explanation for it, and it gives us this particular information. So now, when we are going to do the projection, so in order for us to obtain B, B is no other than the membership function of the output of the system, but B is equal to the projection of mu C A intersected with fxy. But remember, the projection definition that we have seen in several slides ago is no other than the projection over the complement variable of the system, which is here given by x. So we take the maximum out of all the x's of this min type of function here, okay? And this provides us now with the max min that we have seen last time in the form of this particular representation. So that's where that max mean comes from. So it's come from the projection of the cylindrical extension and the intersection of the system, and that's why we call it the max mean composition. So now max mean composition, of course, we can extend it to a larger number of representations. So that could be max product, that could be the plus the sum product. So it could be any, and ultimately at the end of the day, it could be an S, no, T norm, S norm and T norm type of operation ultimately. But for now, the default type of representation is noted here as this type of representation. So we have B now, which is given by A intersected of F. Remember, A is what we call the context. That's the data of the system. And F is the relation. And that's what we have seen last time when we did, I mean, that I, which is the inference is equal to D composed with K. So this is exactly the same as what we have seen in the last set of slides of last time. So now we are generalizing this, and we call it the compositional rule of inference in the general type of case where we have not one single relation, but multi-type of relation. So if we look at the visual representation now, which is very, very helpful to understand this particular process. So here we start with a fuzzy relation that is connecting between X and Y. Remember, this fuzzy relation comes from the many type of relations similar to the one that I just mentioned. If temperature is hot, then air conditioner is very high. If temperature is warm, then the air conditioner is somehow high. If temperature is cool, then air conditioner is negative high. So these type of relations are articulated in this particular representation here between X and Y. So this is one single type of relation, but in general, the relation, I mean, could be between several type of variables, and we cannot visualize it. So here between the antecedent X and the consequent Y, in the continuous case, we have this particular representation. Remember last time, in the last lecture, that particular type of relation was expressed in that format of the table or the matrix. Remember? But we have then some discrete representation of the fuzzy set A and the fuzzy set of the consequence. So discrete type of representation. So here we are generalizing this particular representation not to with discrete representation, but with a continuous type of representation. So this is the fuzzy relation here. And then we have the fuzzy set A here. But fuzzy set A cannot do any type of connections between A and the relation here. So because they are not of same dimension. So we have to extend, we have to do the cylindrical extension of this particular type of fuzzy set to make it a relation that is in the same Cartesian products as the original fuzzy relation. Okay, so we need to do a cylindrical extension. Now, doing cylindrical extension and composing this cylindrical extension with this fuzzy relation, we are able to obtain this particular outcome, which is the minimum of A and B, which is this part and this part. Okay, so we end up with this particular representation here, which is the whole part of what we are doing, and then taking the projection of this particular component of this 3D, we end up with this particular representation of the fuzzy set B, and that is the projection of C onto Y. So this is C here, and this is C of which is the intersection onto Y, basically by taking the maximum over all x's. And this is the membership function of X. So we departed from A here, and we arrived to Y. Okay, and as you can see, so this is the perpendicular type of direction, and this is the direction of the Y equal to Fx when we are dealing with the fuzzy relation. So this is an extension of what we did last time in the discrete representation, and this is the visual type of representation using all these type of operators that we have spoken about. So here we have seen the notion of fuzzy relation, how to compute it. We have seen the notion of cylindrical extension. We have seen the projection of the intersection of these type of compounded relations for the system, so the projection. So all of these type of operators that we have seen before now are coming handy to illustrate and to help us out providing this decision-making process. But this is only one part of what we are going to see next. We are going to expand this representation from one single rule to multi-rule representation. And that's what I am going to speak in the next set of slides. But for now, I would like to give you the opportunity to ask me if you have any questions. Okay, so I don't see any questions here, but feel free, you can continue asking me any time. And then yeah, I'll be happy to respond to you during the lecture. So now let's look at the notion of modus ponens. Possibly you have seen it in the area of discrete mathematics. So now we are going to expand that area of the modus ponens to the fuzzy logic system. So we know it in the area of conventional logic or binary type of logic systems or Boolean algebra, discrete mathematics. Each one of you should have taken a course in this particular area. So we are going to expand this to the area of fuzzy logic system. So let's look at the modus ponens here. So in the area of modus ponens here, so modus ponens leads to inference of truth of proposition B from the truth of A, and the implementation of A implies B. So through the knowledge of the truth, which is the context, and through the implementation of the relation that connects between the implication of the antecedent to the consequence, we are able to get the proposition B. So this is in the area of modus ponens. So knowing A, which is the truth, knowing A implies B, okay, then we are able to obtain B. And I have shown you that now through various type of operations. So this is F, we do the cylindrical extension of A, and then we do intersection here, and then the intersection, then we do the projection, and we obtain it, B. So that has been for the fuzzy logic system. For modus ponens, it's more direct, and we have it in this type of representation. So let's look at how to expand this. So for instance, for an example, in the area of Boolean logic, we have this relationship here. If tomato is red, then the tomato is ripe. So this is a certain type of fuzzy of a rule that tells us a reality. If the tomato is red, then the tomato is ripe. So during our lives, we infer a lot of these type of rules. We construct a lot of these type of rules. Some people who are expert with a certain type of process are very knowledgeable on how to have a machine working. If you accelerate on the machine, it's going to give you the best type of rotation that is going to do more operation, that is going to do more type of more type of ingestion of a particular type of product. So we know how these things happen. So these are the rules, okay? So we describe these rules. This is the knowledge. This is the common knowledge. If temperature is high, then of course we need an air conditioner, if we have one, to be high. So if the temperature is hot, we need, high air conditioner. If the temperature is hot and the weather is humid, we need even higher level of the air conditioner for that particular system. So that's basically the knowledge. That's the knowledge. That's, we call it rule. And then we say that the tomato is red. So this is a fact. If the tomato is red, and then if we have A implies B, which is the relation of the tomato is red, then immediately we infer B. So this is what we have inferred in the area of Boolean logic, where we are dealing with the discrete representation, where we are dealing with the conventional logic. If we have A implies B, and if we have A, then we have B. As simple as that. A implies B. If you have A, then we have B. In the area of fuzzy logic, life is not as discrete and conventional as it is. So it could be that the tomato is red, then the tomato is ripe, which is an excellent type of rule. But how about if the tomato is somehow red? Somehow red. Somehow red. So it's not fully red. And the red is here in this type of representation could take, I mean, a membership function. So the red is going to be a descriptive of the tomato, and the somehow is going to be the hedge of the linguistic description of red. So if the tomato is red, what about the B? Can we say the tomato is ripe? No, we are going to have certain type of operation now for the ripeness of B. So the ripeness of B is going to be affected by this level of the somehowness, if we call it that way, of the red. So that's what we are going to do now in the fuzzy reasoning, how we are going to represent the partial truth. So if we have a partial truth here, what is the conclusion that we are going to obtain given this particular knowledge? So the knowledge is not going to change, the knowledge is going to remain the same, but the truth might be a version of what the original type of expert, I mean, has provided for our system. So the tomato not 100% red, so it's a little bit greenish. So then what should we say about the tomato? Is it ripe? Is it very ripe? Is it somehow ripe? Or is it not ripe? So we are going to look at all these type of inferencing when we are going to do the modus ponens as applied to fuzzy logic case. So this is what we know on the modus ponens for the Boolean algebra. This is what we have known in the area of discrete mathematics. If X is A, which is the facts, if you have the rule or the knowledge is this way, then the consequence immediately Y is B. So there is no issue there. Now, if the premise one is X is a portion of the truth of part of the inference, then we are going to have a B prime. But what is this B prime? How do we compute this B prime? So A prime is part of the truth. A prime could be close to A, B prime could be close to B, but how close it is? Is it the same thing as A prime close to B? So we are going to see how we are going to determine these things, where in this type of representation A, B, A prime, and B prime now are fuzzy sets. So in this particular case, they are discrete entities, whether it's true or it's false. So now we are going to have the fuzzy sets representation. So let's look at this first reasoning for the system where we are doing with one rule and one antecedent. So let's look at this particular system. So let A prime, and B be fuzzy sets over X. Of course, A is over fuzzy set X. A prime is still on the fuzzy set prime of X. And B belongs to the consequent, which is Y. Okay? So, and B prime is going to be also onto Y. So assume that the fuzzy relation implication A implies B is expressed as a fuzzy relation given by Rx. Then the fuzzy set B induced by X is A prime for the relation, so B prime here. So this should be B prime. Then the fuzzy set B prime induced by X is A prime for the relation X is A, then Y is B, is given by the following. So we are going to utilize now the representation that we have seen earlier. So where we are doing the cylindrical extension of A prime, okay, and then intersect with mu R, and then we do the projection of this particular section, and it gives us max min of mu A prime now, because we have the C A prime here, and mu R, it doesn't change. Okay, so this gives us rise to mu A prime and mu R xy. So the minimum of, remember that this is the minimum function, so it's mu A prime and mu R. So I reflect it in this particular representation. But remember, this mu R is no other than A implies B. Okay, so this is A implies B. That's the relation of the knowledge. Okay, so if we are reflecting it in this particular representation, so A prime composed with R here, A prime composed, which is this particular B prime, it's given by A prime composed with A, which implies B. Okay, so knowing of the distributivity of the operation of composed and implication, this gives us the value of A prime composed with A implies B together. Okay, so this is, I mean, the representation of this particular type of system here. We are going to apply all of this type of representation into this particular distributivity representation. So what does that gives us? This gives us the following. This gives us, using the distributivity of the representation, as I mentioned to you here. So this is going to, I mean, as I mentioned here, so we are going to utilize the distributivity here. So this is going to give us, I mean, all the membership function of A composed of A implies B, but this is a minimum over the A, and also this is the minimum between B and the outcome of this particular system. Okay, so this is the minimum out of this particular system. And this provides us with this particular representation if we utilize the distributivity. So now we bring all the variables that are connected with each other because they are over the same universe of discourse and composed with the variable that is over the universe of discourse of Y. Okay, and this particular representation here of mu A prime and mu AX here is no other than the degree of validity, and the degree of validity is given by W. Okay, so because this is again over the universe of discourse X, remember that's the representation that we have seen. So this is X, and it applies to the mu A prime and the mu A of, I mean, the part of the mu A of this particular relation using the distributivity. So this is over the universe of discourse X. This is over the universe of discourse B, of discourse, let me take that one, over the universe of discourse Y. Okay, so by doing the distributivity, because this is over X, so we compute that type of minimum over the X's. And then we apply this particular maximum of the value over all these particular this particular application. So first, what we are going to do, we are going to see the maximum over X of all these, the minimum of between mu A prime and mu A. So that's what we are going to do. So this maximum of X doesn't apply to mu BY. So we are using the distributivity type of relations because we have broken this particular relation. So the relation used to be related here. So because this is function of only X, so we bring it to the mu A prime. And this gives us the degree of validity and minimum as applied to the minimum of mu BY. Okay, so this is, it applies the degree of validity over mu BY. So what does that mean? How do we obtain this particular type of relation when we are using this for one single antecedent? So what does that mean? So let's suppose that this is a hot temperature. Let me give you an example. This is a hot temperature, okay? And this is somehow hot temperature. This is somehow hot temperature. So it's a version of A. So it is a version of A. This particular intersection between A and A prime provide us with the value here. So the minimum of A and A prime is given by this particular type of representation. So this particular element W here is going to be projected, mapped into the consequence membership function. And now the membership function is going to fill up only up to the value of B, because that's the minimum of omega as applied to mu by. So that's the minimum as applied to this particular function. So the value of the degree of validity is applied to the membership function at the consequence. And that particular type of consequent now, this, instead of being a trapezoidal membership function, it's going to be a shorter version or smaller version of B, which is becoming the B prime. So the blue part is going to become the consequent of the system. So given the truth or a fact or the context, X is equal to A prime, because I mean the sensory system has measured the value of A prime. So the A prime has been projected and intersected with the original value of A, and it gives us the value of omega, which is going W, which is going to be reflected on the consequent. And so this is the air conditioner value. So instead of having, I mean, full air conditioner value of the system here, we are going to have only 70% of it. Why? Because the temperature is not hot. The temperature is only somehow hot. So it's warm. The temperature is warm. Okay? Somehow hot, and it's represented in this particular type of relation. So this is how we are able to replicate and how to obtain the output of a system when we are dealing with the fuzzy reasoning. So this is what is known as single rule with single antecedent. So this is single rule. So one rule. We have one rule and we have one antecedent in this one antecedent, which is A here. Okay. So that's the first simplest case for fuzzy reasoning. So this is a representation, and this is going to help us out develop, I mean, for the more complex type of representation. Okay, so before I go to the more complex system where we are going to have single rule with multiple antecedents, so instead of having only temperature as antecedent, we are going to have temperature and the humidity that are going to let us know how the air conditioner is going to feel. So now we are going to compute these two type of systems for two antecedents. But before I go to the next set of slides, I would like to take some questions here, if you have any, please. Okay, so I don't see questions here. Again, if you have some, I mean, please think about them and then let me know what, and I will be happy to respond. So now we are going to do with single rule. So this is one single rule, still one single rule. But remember here now we have two antecedents. So the rule now it says if X is A and Y is B, then Z is C. Similar. If temperature is hot and the humidity is high, then air conditioner is high. This is an example. One part of the knowledge base. Remember, the knowledge base is usually composed of many rules. So we are looking at one single rule here, and we are going to extend later on with multi-rules with multi-antecedent. So the premise of the system, which is the fact, which is the context, temperature is not high. Temperature, the humidity is not high, so they are version of the truth. So they are version of the truth. This is the rule that we have here. So this is the rule, part of the knowledge base. And we would like now to capture what is Z. So Z is C prime. How to compute this C prime, which is a component or variant of C, utilizing this truth or this context and the knowledge base. So this plus this, okay, is going to give us C prime. Okay, so let's look first, I mean, at the relationship now that is combining between two antecedent and one consequent. This relationship now is going to be in the three type of dimension. So we might not even visualize it, because remember that when we have, I mean, A Cartesian product B, remember that the relation is already in the three-dimensional case, in the 3D. So now when we are dealing with A and B and C, then it's going to be in a fourth dimension that we cannot visualize it at this particular stage. So this is the relation that is connecting between the antecedent to the consequent. So the relation is given here when the Cartesian coordinates, the Cartesian product is going to give us the minimum of mu AX, mu BY, and mu CZ. Remember that when we have A Cartesian product with B, it's mu AX and mu BY, the intersection, the minimum. Now we have a relation with the three components, mu AX, mu BY, and mu CZ. Okay, so it is, I mean, three dimension that is representative in the space. It's going to be four-dimension space, and we cannot visualize it. So the results here, this is the truth, this is the context. That's what the sensor has measured at a particular instant of time. And this is the relation. This is the knowledge. Remember, this is the knowledge. And this is the data in what we have seen last time when we have done decomposed with K. So now we are going to the more complex type of representation for this system. So now let's open up these type of representation, the Cartesian products, and in the form of the membership functions. So this is represented in the form of membership function mu A prime and mu B prime. So that's the Cartesian product. And this is occurring, I mean, as the Cartesian product of A and A prime and B prime. The composition, we know that it is a minimum type of operations. And then the Cartesian product here also is a minimum type of operation that connects mu AX, mu BY, and mu CZ. So now we have all this type of representation, and now we are going to collect using the distributivity type of operation for the T norm and the T conorm to compute this type of representation. So first, when we are doing this type of composition, we do this with this particular composition, we are going to do it using the max min. And the max min here occurs for the two type of variables that are in the early part of the equations. So that's why the max min over x and y here, okay? So then we continue max min of this, and then we use the distributivity type of operation, and then we would like to connect the x's and connect the y's together. Because, I mean, the x and the y here do not make any sense to combine both of them. So we connect the degree of validity for the x's, and it gives us the degree of validity of omega 1, and we connect the 1 for the y, and it gives us the degree of connectivity of 2, and then the connection between both of them, we look at the minimum between this one and omega 1 and W1 and W2. And all of it is applied to the consequent variable. So earlier we have seen that it's mu A prime x and mu AX applied to mu CY. Now we have two antecedents for which we are going to do the same type of operation, and we are going to have degree of validity for one, degree of validity of the second one, and then we have to do the composition of both of them, and this gives us what is known as the firing strength. So the firing strength is no other than the minimum of W1 and W2 as applied to mu CZ. Okay, so now we are expanding the rule to two antecedents, to x and y. Okay, so when we are doing it for x and y, then we are going to do the same type of operation. Now, the good thing about this, that this is a generic type of results. So if we have now x, y, w, and whatever, I mean, let's say x, y, w, and then the consequent is z, then we are going to obtain the same thing. We are going to have omega 1, omega 2, omega 3 for w, okay, as applied to z. And we can do it for n type of antecedents and for one consequent. For this particular system here, we are only using multiple antecedents with one single consequent. If we have some time later on in the course, I will give you one example where we have two types of consequent with the fuzzy system, but usually we don't control systems with two variables at the end using fuzzy logic modeling. So we utilize one output at a time, and we develop another fuzzy logic system for the other type of variable, and then we connect them through certain type of relationship between the control variable 1 and control variable 2 of the process, which is not part of this course. So this we tackle it in a more advanced representation of fuzzy logic system. So this is what we have obtained. Let me look at the visual type of representation here. Okay, so this is what I just mentioned to you. For n antecedents, we have, I mean, the firing strength is going to be omega 1, omega 2, omega n, the minimum of all of them as applied to mu CZ. So let's suppose that this is the version of the truth, x is A prime and y is B prime. So this could be temperature is somehow hot, and the humidity is low, which is, I mean, intersects with the humidity of B. So the original representation is A and B and C. We are applying to this particular original rule here, we are applying the truth, or what the sensor provided us at a particular instant of time, the values. Because as you know, in a temperature control system, the temperature could change anytime when you have more people or when you have an open window. So the temperature could change, and then the controller has to adapt and has to change the value of the air conditioner as the temperature is not within the regulated value of certain, certain a priori type of value. Okay, so if you set up the system at 72 degrees Fahrenheit, for instance, and because there is an open window during the winter, then you have a temperature becomes at 50, then the system has to regulate itself, and it's going to go and ask the air conditioner to provide us with a negative type of low, which means that it's providing us with some heat. So now we look at the intersection of A and A prime. We look at the intersection of B and B prime. So one is providing us with omega-1, the other one is providing us with omega-2, and look at what we are computing here. So this is a T-norm. We use the T-norm usually as the minimum for the default, but we could utilize the product here. We could utilize, but if I don't tell you anything, utilize the min as a default. So in an exam or in a quiz, I might ask you to provide the fuzzy reasoning using the product. So what you are going to do, then instead of having the minimum of omega-1 and omega-2, you are going to utilize the products of omega-1 and omega-2, which is going to hit this particular type of outcome of the C of the Z output of the model. So this is one representation for the model. So you have the knowledge, which is given by one single rule here in this particular case. You have the fact, which is given by two antecedents values, and then the consequent is going to be computed by taking the minimum coming from the antecedents of the fuzzy rules, and it's given here by the value of C. And this, once you have obtained this omega here, this is going to affect the output of the system, and it's going to give us this clipped version of the output of the system. So now you tell me, how can we compute what's in here? That is going to be the next part of this module. What type of fuzzy inferencing we are utilizing. For now, we are talking about fuzzy reasoning. The fuzzy reasoning, how to imply from the truth, which is given by A prime to B prime, how to generate the value of C prime. So we have to go through this step, and then through this step to arrive to this step for this particular location. Okay, so the next part of the lectures, I mean, possibly next time, it's going to be what is the representative, what is the center of gravity. We are going to see the center of gravity as one of the representative of these particular representation for the system. So this is the general case when we have one single rule. So now we are going to go to the next, even more general, which is the most general representation for fuzzy inferencing system, where we have not one single rule, but now we are going to have multiple rules. Rule 1, Rule 2, Rule 3, Rule 4. So now it's going to express something similar to this. If temperature is high and the humidity is high, then air conditioner is high. We go now to another rule, and it says if temperature is low and the humidity is high, then air conditioner is medium. If temperature is low and the humidity is low, then air conditioner should be negative low, which means that you have to generate heat. So all of these type of rules are going to describe the truth about your process. What is happening? What are the possibilities of all these type of occurrences happening within a particular room? And all of them are legitimate. Sometimes we have cold weather. Sometimes we have a lot of people in a room. Sometimes we have a hot weather. Sometimes we have a lot of humidity. So we have to express all these type of occurrences within a particular system so that our knowledge base is not missing any particular type of occurrences. And later on, we are going to see that the impact of rule 1 is different than the impact of rule 2, different than impact of rule 3, impact of rule 4. So each one of them is going to have a weighted version of the execution of one particular rule. And that's what we are going to see in the next several slides. Okay, so now this is the most general case where we have multiple rules with multiple antecedents. So we are going to presume that here we have only 2 antecedents, 1 consequence, but we have 2 rules. As you can see here, this is different than the earlier case. So it is similar to the earlier case where we have 2 antecedents, but here we have 2 rules. Now look, we are now dealing with 2 types of rules. One is expressed by a relation R1, A1 cross B1 implies C1, the other one R2, A2 cross B2, C2. So we are going to utilize the distributivity type of operation over the union for the max-min operator. And we are going to extract what is the outcome for this particular system and how we are able to create this C prime type of representation. So now we have the truth. This is the context. This is the knowledge. So remember, the knowledge K now is given by the union of all the representation of what could it be in that particular system. Remember so far, from last lecture and from this lecture, we have seen only one single rule. We have seen only one relation that describes the knowledge. Now we are going to see more of this knowledge. So now the knowledge could be R1 union R2. So when we have 2 type of rules together, we have to accommodate both of them. So both of them have to execute at the same time. So both of them, this one and this one, have to execute. So we have to have the union of this outcome and the union of this outcome. And we have to find it out what is, I mean, the overall, I mean, part that is going to be due to these 2 type of rules. So while these rules are going to be executed together, they are going to be a union of all these type of rules. They are occurring at the same time, and each one of them is providing some sort of knowledge. So let's look at this particular knowledge. So this is what we have seen in the earlier case that we just seen, when we are dealing with multiple antecedents, but with one single rule. So we have 2 rules here, rule 2 and rule 1. Okay, so rule 1 with multiple antecedent, rule 2 with multiple antecedent here. So now the outcome is going to be C prime 1 and C prime 2. But what is union? So the union is going to be the maximum of C prime 1 and C prime 2. So we are going to combine both of them together. And the C prime is the inferred consequent of rule I. So this is C prime I is equal to A prime Cartesian product with B prime composed with Ri. So this is what each one of the rules provide us. So you can see this AI here, and this is mu BI here. So this is for each one. This is related to the ith rule, and this is the ith rule. And we have seen in the earlier set of slides that when we have one single rule, this is how we are going to compute it. So the system is going to provide us with all combination of all these type of elements. And this is the C prime 1 union C prime 2. So we can now, with n rules, we can have C prime 1 union So this is C prime 2 union C prime n if we are dealing with n rules. And this gives us the most general type of representation for a particular type of system that is composed of several if-then rules in the fuzzy logic representation. Let's look at it now in the visual type of representation. Rule 1. Rule 2. This is the context. This is the data. So I call it context. What does that mean, context? Is what the sensor measured as at a particular time. So these are working all the time, and now we are exciting them with what the system provides us at a particular instant of time. So let's look at it here, okay? So for this particular A prime is going to affect rule 1 and affect rule 2. This one is affecting rule 1 and rule 2 at the second antecedent. So this is the first antecedent, and this is the second one. This is the consequence for rule 1. This is consequent for rule 2. So let's see what we are going to obtain as the outcome. So this is the input, the context. We depart from here. Okay, and we arrive to this. So we are going to do this set of operation. But we go through them, I mean, through this yellow type of presentation. So we do for rule 1. So this is what the system, I mean, the firing strength here. This is a firing strength here. This is the degree of validity here. This is another degree of validity. And we found with the minimum T norm, the firing strength for rule 1. So it gives us a clipped version of C1, which is this. The same thing for rule 2. This is the degree of validity here. This is the degree of validity here. And then it gives us a value of omega 2 here for this particular version. And then we are obtaining the clipped version of this. And then what we do, we assemble these two using the union operator. And of course, the union operator in the format, it's an S norm. So it could be the max, or it could be any S norm. Okay, S norm. So let's look at the max when we are adding this one and this one. So that one and that one provide us with this particular membership function that is given here. Sorry, we redo that. So it gives us this. Okay, sorry for the thing. So this is the membership function that is representative of Z as being equal to C prime. Okay, so this is the most generic. So now we can extend this not only to R1 and R2, but we can extend it to N type of relations, and then we try to obtain the compounded version. Okay, so this is what is known as fuzzy reasoning. So we started with the first case where we have the system with one single antecedent, one single consequent, one single rule. The second case is two antecedents, one consequent, one rule. The third case, the most general one, multiple antecedents, one consequent, multiple rules. Okay, and we have used the distributivity operations of the max mean with the union operator, and we were able to extract this particular type of representation. This is, I mean, very visual. This provides us, I mean, I try to explain it to you mathematically using the max mean operation, this intersection of relations, and how to utilize the cylindrical extension, how to utilize the projection in order for us to have not only a visual representation, but also mathematical understanding of what these rules mean. By the way, these type of implementation are occurring up to this day in some of the most sophisticated train systems around the world. One of the most sophisticated train, I mean, is residing in Japan, the subterranean system, and it is working with something similar to what we are developing here. They are based on fuzzy inferencing mechanism. I mean, of course, it's much more complex system than this one, but they are still using, I mean, fuzzy inferencing mechanism that has been developed in the 80s, the 90s, and it has been performed in the 2000s, and up to this day, people are utilizing version of this particular type of fuzzy inferencing and control inferencing system. Okay, so this is what I have discussed with you so far. So I would like to take any question here if you have any before I proceed forward on the fuzzy reasoning and fuzzy inferencing part. Okay, so I don't see any inquiry here. So this is what we are going to do for the fuzzy reasoning. So this is the general representation of fuzzy reasoning that we are going to speak. Now we are going to see what means this fuzzy reasoning. What does it provide us? Okay, so the fuzzy reasoning has a number of steps. Okay, so first of all, obtains what is known as obtain a degree of compatibility. Compare the known facts, that's the sensory version of the system, with the antecedents of the fuzzy rules. That's how to map the truth to the rules. This is what is known as degree of validity. When we have seen it for one particular antecedent, we have seen that's the degree of validity. When we have seen it for two antecedents, we have seen that it is the firing strength. Okay, so find the firing strength which combines the degree of compatibility using fuzzy and or. Most of the time we are utilizing the AND operator when we are dealing with fuzzy logic system. Rarely that you have a system that are utilizing the OR. If we have the OR, then all the AND operators that we have seen earlier are going to be changed to the maximum type of operation, which we don't use. A lot of the times, I mean, all the rules are in the form of if something, and if something, and if something, then you have something. And that's what we are studying here. And that's what we are going to focus for this course. And that is going to be included in the assignment number 3 or in the quiz. So we are going to utilize only degrees of compatibility using fuzzy ANDs. Okay, so we don't utilize the OR. So the OR is not going to be part of any type of things. But this said, there are sometimes in certain type of processes where some of the variables require the connotation of OR. And if it is the case, then we have to adapt the operations that we have seen earlier to comply with the OR. So this type of firing strength indicates the degree of weight at which the precedent part of the rule is satisfied. So here, the compatibility, it means that's the intersection of that antecedent with the truth. Okay, so that's basically what we have. So that's the compatibility. That's the degree of validity for the system. And once we have, I mean, this obtained, then we are going to apply it to the consequence, which could be, I mean, fuzzy membership function, and that one is going to be the firing strength. So when we go from the antecedent to the consequent, we call it the firing strength. That's the degree at which the antecedent part of the rule is satisfied, and then it applies to the consequence. Applying the firing strength to the consequent membership function of a rule. So once we have the firing strength from the antecedents, is going to be applied to the consequence. Okay, so this is what is known as the qualified consequence. Okay, and then the overall output membership function aggregates all the qualified consequent membership function to obtain the overall membership function. So that's what we meant by fuzzy reasoning. So again, let me explain this. So this is compatibility 1. This is compatibility 2. This is the firing strength value of omega 1. And this is the qualified consequent. Okay, so the qualified consequence. And then the aggregate 1 is going to when we apply all the same thing, the qualified consequent, to as many rules as we have in the knowledge-based representation. Okay, so that's what it is the fuzzy reasoning. So you have a fuzzy input and you have a fuzzy output. So far we have only fuzzy output. So now we would like to go to the next level. How can we extract this qualified consequence and make of it a discrete signal? Because so far we have only resolved half of the problem. The remainder of the problem is going to be in the form of how to obtain that particular type of representation. So this is a fuzzy reasoning example that, I mean, we ran on MATLAB some years ago. This is an inverted pendulum where you are controlling the angle, where you are controlling the velocity. We have rule 1 here. We have rule 2 here. We have rule 3 here. And this is rule 4 here. Okay. So for each one of them, so we are obtaining the compatibility here, level of compatibility here, and this is the firing strength is applied to the qualified consequence. So the qualified consequence is this part. Okay, and then the aggregate consequence is going to be given by this particular area, and this one is what we are going to compute later on. That's the discrete type of signal. So for now, I mean, disregard it, but I would like you to look only at the blue version here of this particular graphical interface for this particular system. Okay, so now let's look at what a fuzzy inferencing system does and how we are obtaining all these particular representation. Remember, this is the knowledge base composed of if-then rules. This is the aggregator. Okay, the input could be fuzzy, it could be crisp. If it is fuzzy, then we are going to, I mean, use the intersection with the corresponding type of antecedent. If it is crisp, we are going to fuzzify it so that it is being applied to the antecedents. So the basic structure of any fuzzy inference system is made by a rule base, by database of rules, and by a reasoning mechanism. And this is what we are going to see in the next version of the system. So this is the reasoning mechanism that we are going to tackle in this particular type of representation. So the rule base, database of rules. So this is the database of rule, the rule base of the system, which is the K here. The aggregator, we have seen how to compute the aggregator. So this was an excellent thing that we have done so far. But now we are going to look at the notion of defuzzifier, because that's where we are going to extract the decision signal. This is where we are going to extract the crisp signal of the system. Okay? Fuzzification refers to the representation of a crisp value by a membership function. So fuzzification refers to the representation of a crisp value. So let's suppose that we have a crisp value here, okay, given by this particular signal. Fuzzification means that we are going to fuzzify it, give it a membership function. Okay, so if you are dealing with a crisp value, the membership function is going to be a function that has, I mean, a width of 0, but it has a membership function which is given by 1. So this is what is known as the fuzzy singleton. Fuzzy singleton. And this is going to become very handy later on when we are going to do the fuzzification. What does that mean, fuzzy singleton? Remember in the earlier slides when we spoke about all these types, let me go back to one of the pictures. When we spoke, so this is the A1, this is a fuzzy set, A1, the blue one. But the green one is a fuzzy, the A prime. But how do we obtain a signal from a sensory system that is fuzzy? That doesn't make sense. So usually a sensor is providing us with a voltage. A voltage value is namely a discrete value. So what we do, in order for us to elevate a signal from the value to intersect with the membership function, so let's suppose that this is a membership function, And then our sensory system has measured a value at this particular location. How this particular location is going to intersect with the membership function? This is going to be done through the fuzzy singleton. When we do the fuzzy singleton, then we can see the degree of compatibility occurring there. So that's why when we are dealing with discrete values of a sensor, the first thing that we do is to create the fuzzification, and the fuzzification is provided by this particular concept. Okay, so fuzzification refers to the representation of a crisp value by a membership function. It is needed prior to applying the compositional rule of inference when the data measurements are crisp values. We cannot utilize none of what we have seen in the fuzzy reasoning or the compositional rule of inference if those values that are discrete are not elevated to the level of fuzzy variables to make them fuzzy singleton. Okay, so this is not so in general, I mean, in terms of the fuzzification input, because there are some fuzzy sensors that are created nowadays, but for many industrial type of sensors, the system is providing you with a discrete type of data, which it has to be fuzzified. And fuzzified, when you mention fuzzified, is going to be on the fuzzy inferencing representation. So it meets the membership function at a certain type of location for that particular level. So there are many type of the level. So there is the what is known as discrete case of fuzzification, continuous phase of fuzzification. There are many type of fuzzification procedure. We are going to look at only at the singleton method. So I'm not going to look at the triangular function method. I might look at it after later part in the course when we have some time. So I will go back to this particular area. So I'm not going to look at the discrete case of fuzzification. I'm going to look at this particular singleton method where when we have, membership function, where we have, this universe of discourse, and if we have certain type of discrete values for the sensory measurements, then we elevate them to membership function values to become equal to 1. To become equal to 1 when we measure them. And that's what is known as the singleton method. So I will skip all these type of fuzzification and I will stick with the singleton method. So the singleton method at the value of the measurements of y0. So if we have some values here where the sensory measurements have measured the value of y0. So we create the Dirac type of impulse here with magnitude equal to 1. And we put it as is equal to 1. So this is equal to 1 when y is equal to y0, and it is 0 elsewhere. This is what is known as the singleton method. Okay, so these are what is known as the singleton method for the system, where we are presuming that the measured data is very precise. Okay, if it is in the case it's not very precise, it's going to possibly take a certain type of interval around this particular region, and then we expand the delta to certain region here. Okay, but we don't do it usually. So we presume that in all the contexts that we have here, the singleton is an impulse with width equal to almost 0. Okay, so that's basically what we are going to utilize, and that's what we are going to use when we are going to see the defuzzification representation in the next lecture. So yeah, there is a possibility that next lecture I will post it asynchronously. So that is the lecture of Monday. And I might even post it even before Monday, for you to look at it and to read from it. But it will be available at least, at most on Monday. So and I will let you know if I post it even earlier, possibly Friday or Saturday this week, because we don't have a Friday lecture. So we don't have Friday lecture, and we have the Monday lecture next week, which I am going to post asynchronously. But I will let you know about this. I will send you a chat about this, and I will let you know whether it's going to be asynchronously or synchronously, to let you know whether to attend here or not. Okay, so that's what I wanted to share with you for today's lecture. I would be happy to answer any of your questions. Please feel free to email me. And if you have some issues with any components, My textbook, chapter 3, has excellent material which goes into the details of what I just spoken about today. So it gives you the details, it gives you some explanation if you would like to read a little bit more about it. Okay? So I let you go now. So and then if you have again some questions, let me know and I will be happy to answer them. You can also send my TAs and they will be happy to respond to you. Thank you again for your attention, and I will see you next, in my next lecture, whether it's asynchronous or synchronous, and I will let you know about that one. Thank you very much and have a good day.